Hello everyone. In the last video I said we'd be working on the cylinder head right now. Well, I took it apart, cleaned it up, removed the broken stud, went out and bought a set of metric taps just to clean out the threads, and discovered it needed more parts than I figured, which I have ordered, and they'll be here tomorrow. So, in the meantime, we can keep working on the block, because I got the bolts. Complete set of lower crankcase bolts from the dealer. I went back to the dealer and tried to get the rod bolts. Problem was the person at the parts department actually argued with me that these bolts do not exist. So I bought a set from zzperformance.com, which are also genuine GM. So we got plenty to do now. So I don't know if I've mentioned it or not, but these are torque to yield bolts. Now, there's a lot of superstition behind these. A lot of people don't really understand what they do. The torque to yield bolt, it's like a traditional bolt in the sense that you torque it down and it holds the casting on. But these, when you give it the additional degrees of turn, it loads a spring tension. These are actually, they actually have some spring to them. And that's made to compensate for the travel and expansion and contraction with heat and stress, where everything can move around to a certain point, but will return to the same place when it started. Very precision, and because of the spring effect, they're compromised every time you use them. So, long story short, they can only be used once. Now, some people have told me that this is all just a conspiracy to sell parts, which I don't know, but I would say if GM is just trying to sell more bolts, I think there'd be a lot more of them would need to be replaced. They'd be a lot more available and would cost a lot more. But whether you believe in it or not, the manual said to replace them, so I'm replacing them, and I'll have a clear conscience when I'm done that I did the job right. Now, to make sure I'm getting a proper 70 degrees of rotation, I'm actually using some kind of measuring device this time. These bolts actually take noticeably more effort to turn than the old ones back when I plastic gauged it. The connecting rod bolts get 18 pound-feet of torque the first time around, and .100 degrees of rotation the second time around. It's halfway between the 15 and 20 mark, so it's probably in the neighborhood of 18. Now it's time to install the oil pan. Now, I'd like to point out that this also does not use a gasket. It's glued on with gasket maker. Also, this part right here is the intake for the oil pump. So it's important that it seals and that it's not clogged. This is the corresponding oil pickup hole on the block. All the bolts are the same, except for one really long one that goes in the back. A new rear main seal from Felpro. This particular seal didn't come with instructions, but the general rule is you want to put some kind of lubricant, like engine oil, on the surface on the inside. I also put a little bit of gasket sealer on the outside, even though it probably doesn't need it. Now these engines, usually on most modern cars, I use a one-piece seal. There's a big plate that goes on the back here, which this would be connected to. But this is how it goes together on the Ecotec. And this part on the seal needs to be tucked in. It's fairly simple. Okay, I just learned something. When you have the block sitting normally, the seal is all but impossible to install. But standing it on the front, facing down, with gravity working for you, it practically puts itself on. And yes, I did use the old trick of using the old seal, and a block of wood, and a hammer. And now back to the cylinder head. Currently I'm working on reseating the valves. Now my original plan was to just reuse the old valves. I figured the exhaust valves would have some pitting to them, but would be reusable. Now the first two I looked at were just that. You can kind of see that. They do have some pitting to them, but it's not very deep, and it wouldn't really make much of a difference. The first two look like that. Then the third one I got out was considerably worse. The pits in this one are much deeper. In fact, that's not a lump of dirt, that's an actual pit in it. The other two could be ground smooth, but this one, before you got that out, it would go through the margin on the valve. So this one was shot. The intake valves are like new all around. So after looking at that exhaust valve, the decision was made to replace all of the exhaust valves. Now the cheapest way around that was to just buy a complete set of valves, which I did off Amazon. So all 16 of them are brand new. And I'm not going to throw away the old intake valves because they're still good, but I'm replacing all of them anyway just because I have them. So one at a time, I'm lapping the valves to the seats. It's a fairly simple process. Now usually with doing this, the standard way is you grip the valves with a suction cup. They don't really work on these valves because of the rough surface, so I have a bunch of butyl tape on this that grips the valves pretty well. The first thing I want to do is clean the oil off the valve face. They're coated with oil so they don't rust over while being stored. And that's how you grip them. Now the first thing you can do is just take a felt pen and put various marks on the valve seat to see if the valve is contacting the seat all the way around. And wherever it's touching, the mark will be removed. As we can see here, the valve is touching just about all the way around, which is pretty good. Now that step was not really necessary on this engine because it's so new and so nice. A lot of these problems I keep talking about to look for are really a problem with older engines, like antiques, ones that have been mass rebuilt, parted out, pieced back together, and have had who knows how many unknown artists working on them. Now, an engine like this was running just fine and it's never been apart, so you can just assume everything is still good on these. So the next step is we'll start lapping the valves. Now generally there's two kinds of compound. There's the coarse and the fine. Normally you start with the coarse and finish up with fine, but since the valve seats are in such good shape and the valves are brand new, we're just going to go once around with the fine stuff. In fact, even this step is arguably not really necessary. Valve seal is really critical on engines that idle at a very slow RPM, like 400 or less. It's critical for a very smooth, stable, consistent idle, but an engine like this, I'm not sure the difference would even be noticeable. So, start lapping them in. After a while, the tone of the cutting changes, and you know the compound's worn completely down. That's probably good enough. What you really want to look for on the contact of the valve and the seat is a line going through the contact surface. Now obviously this has none of that because everything's in such good shape, so I'll put it back together as is. Brand new valve seals, which I also got from Felpro, a complete set. This is a very common cause for excessive oil burning. These get old and just start rotting away. It's a good idea to replace them whenever you're removing the valves. Installing the valve keepers on this head is pretty tricky. This is a traditional tool I've used on just about everything, and it won't work because the valve springs are pretty deep inside the head. So I got another valve spring compressor, which also didn't work. So I took part of that and made it into an extension for this one. And not the best way, not the most elaborate way, but didn't really cost me anything. There's no sense in spending big money on a tool just for this that I'm only going to use once. Installing the valve keepers are really tricky on this because they're so small. What I've been doing is gluing them to the valve stem with gasket maker and putting them on using two screwdrivers as chopsticks essentially. And I'm not going to film it because it's very fussy and takes a while, but that's the best way I can describe it. And they're installed. Alright, did all that 16 times and we're done with the valves. Next we're going to check the cam lift. Now what we're doing here is measuring wear on the cam lobes and consistency between them. We want them all to be pretty similar. Now the exhaust may have a different setting than the intake, so they don't really need to match each other, but they need to be consistent on each side. Now to do this normally, you use a 0 to 1 inch outside micrometer and measure the smallest point of the lobe, and then measure the biggest point of the lobe and subtract one from the other, and what's left is the amount of lift. Now I figured out a faster, easier way to do it. I have a dial indicator on a stand. Now the stand is magnetic, so it works with iron blocks, but Since this is aluminum, I'm just going to have to hold it down. It's not the most precision way to go, but it'll do for my purposes. And then I'll just rotate the cam. $100, $200, $30, $35, $36, and now it goes down. 236 thousandths of lift. So I'll check the rest of them and see how consistent they are. I've measured the lobes on both camshafts, and on the exhaust it ranges from 234 thousandths to 236 thousandths. Most of them are 235. The number 2 cylinder, front and rear, are the lowest at 34. The number 3 front lobe is at 36. So that's the exhaust side. On the intake, every single one of them measured 35, or 235 thousandths lift. So they're all right on target. The book recommends no more than 1/2 thousandth or 5/10 thousandths variation between the lobes. So intake cam is good. The exhaust cam didn't really quite pass specifications, but I mean, this could be from my technique. May not be very precision, but even if that's the case, I'm going to reuse it anyway, because 2 thousandths is just not worth buying a new cam for. And now the adjusters and rocker arms. Now, I took these out. I labeled and bagged each one individually, which is a good idea if you're going to reuse them. That is the adjuster. It works just like a hydraulic valve lifter on a conventional cam and block engine. A rocker arm, which uses a roller. The indentation goes to the adjuster, the other end goes to the valve. Now, just like the main bearings and rod bearings, it's important that these caps do not get mismatched or put on backwards. Now, on this particular engine, they numbered them and put arrows on them. So that's kind of cool. The book calls for 89 inch-pounds of torque on these bolts, but my inch-pound torque wrench only goes up to 80, so I'm stopping there. The intake camshaft rear bearing cap is also part of the flange for the power steering pump, and it's outside the engine. So even though the book said nothing about this, I put a little bit of gasket sealer on it. Not very much, because I don't want it to ooze into the bearing surface. And aligning this is not really a problem, because it's already got these alignment dowels in it. and 18 pound-feet of torque. Finished with the cylinder head. Got it done, got the brackets, the ground cable, a bunch of other stuff on it. Sitting on the engine temporarily, I don't have a head gasket or a set of bolts. I've ordered them and they're on the way. I also need to order a bunch of stuff for the drive chains and see what else I forgot to order. That's all going to take, I don't know how long before it all gets here. So in the meantime, I've got a whole bunch of stuff to clean, and in the next video, we should be able to finish the engine and maybe start installing it. So, we'll see you then.